Okay, bearings. So 3 things you need to know about bearings. They are always from the north, they're always 3 figures, and they're always clockwise. So it's something to always think about when you're going for these questions. The diagram shows positions of 2 lighthouses, so these are where the actual lighthouses are. These are just the north lines added on for you, so you can draw on them. A ship is on a bearing of 70 degrees from A. So a ship that you don't know is on a bearing 70 degrees from A. So put the cross on the actual position lighthouse, go around 70 degrees, mark it off, and then draw a line as far as you can. I'll just go all the way. Okay, you might have to go over here. A ship is also on a bearing of 320. Okay, so just think about this. If that's what we've got B, and that's the north, it's going to be 320 that way round. If it's out of 360, then it's already gone 320. That means this way would actually only be 40 degrees left. So if I do 40 degrees from this way, clockwise, it's the same as doing 320. So I'm going to do 40 degrees there, and cross over. Mark the position with an X and label it C. So X and C, that's the position where these 2 ships will cross. Okay. Again, remember that if I had a full protractor, I could have done it just all the way around. I'm just going to label on my angles as well. So that was 40 degrees that way, wasn't it? Okay. Alright, simplifying a more complex fraction, algebraic fraction, means I'm going to have to do some factorising. If I look at this one, this is a basic factorise question at the top, so I'm just going to factorise that. So think what's common to 7 and 21, that is 7. What's common to x squared and x, that is x. 7x times something is 7x squared, so that's going to be an x, and 7x times something is 21, so that's going to be 3. Then I'm going to factorise the bottom. So front times back, so the front of this is 1, so 1 times minus 15 is minus 15. I'm going to do the factors of 15, so 1 and 15, 2 doesn't work, 3 times 5, 4 doesn't work, 5, I've repeated myself, so I've finished. Because it's a negative here, which one or which pair have a gap of 2? So that means I'm going to select these 2. And then what I'm going to do, the whole point of that was to split this expression into 2 different ones. So one of these is going to be a minus, and I have to make positive 2. So that means the small factor has to be a minus. So x squared stays the same. Minus 3x, put the minus first, plus 5x minus 15. And then we split it into 2 separate little expressions that we can factorise. So I'm going to have x minus 3, and then 5 and x minus 3. And the reason I know that's correct is because the bracket is the same. So we'll take that bracket out as a common factor now. And that'll leave x plus 5. Okay, so if I put that back in the original one, I've got x minus 3 and x plus 5. And the reason I know I'm on the right track is because this bracket's the same. When that's the same, I can cancel it out to leave 7 on the top, 7x on the top, and x plus 5 on the bottom. And that is the final answer. So that's the answer, the simplified answer. Okay. Right, question 16. It could be anything really. You've got to really extract the information. So BCD, and ADB are isosceles triangles. So let's mark that on. That means these are the 2 longest lines, so these are the base angles. So this is the same as y, because that's the base angles of this isosceles triangle. And this is the top angle. Okay, so these 2 are equal because they're isosceles. And if I very quickly do that, 180 take away 120 gives me 60, and 60 divided by 2 is 30. So it's 30, 30, and I used that angles in a triangle equal 180 degrees. And then that, so I was reading email there. I also used that base angles on an isosceles triangle are equal. Okay, so that's what I've used so far. So that's all I can get from this at the moment. I don't know this. I don't know anything else at the moment. So let's have a look. AD is parallel to BC. Okay, so if they're parallel lines, it's going to bring all sorts of different things in here. It could be interior angles, could be corresponding angles, could be alternate angles. Okay, and there's a few ways that you can go about knowing which one that's going to be. So let's have a look. Work out Y. So if I know this one, I can figure out Y using isosceles triangles. And there's a few ways I could do it. I could do interior angles with this. So this could be this and this are interior of these parallel lines. So 120, and all of this would have to make 180, so that all of this would be 60. So this would be 30. Or I could do that I've got this alternate angle here, which I think I'm going to do. This alternate angle, and some people say Z angles, but saying Z is going to give you nothing. This is an alternate angle, so this one is 30. So I'll best write that down. So alternate angles are equal. So that's Y. What's that? DBC is 30. And now I can do the isosceles triangle rule again of 180 take away 30 is 150, and 150 divided by 2, which is 75. So Y is 75. Okay, so a few things in there. It's a nice question. I think that's probably a good exam question to have a practice with, because it involves a few things. And if you understand that one, then you're probably going to be alright with most of the questions you run into for that. Okay, circle theory. You have to know your circle theorems really, and if you don't know what they're called, you're going to lose half the marks already. So we need to just think about the different ones we've got, and just think about what's in the question. And it might give you a clue to what ones you're going to be using. So these are all points on the circumference. These are all tangents. So as soon as it's saying tangents, I'm thinking that tangents meet radiuses at 90 degrees. That could come in. It says these are on the circumference, so they're definitely touching here and here and here. MON is 110, so that's 110. We've got angles around a point, so that we could do something with 360 there. I've also got this kite shape here, which is a four-sided shape, and that means that if I've got these two angles, which I think are 90, I can find this out. Okay, so there's loads of different ways, there's loads of things to include here. So work out BAC. So BAC is that's what I'm after in the end, that angle there. I'm going to add the information I know. So these are all 90-degree angles, both sides. And the reason they're 90-degree angles is because tangents, so write it down, tangents meet radii, you can put radius, it doesn't matter, at 90 degrees. So that's why they're all 90 degrees. If that's 90, that's 90, and that's 60. This four-sided shape you can see here, the kite that you see, they do make kites a lot with these two tangents doing this, is going to be at 360 degrees. You've got two 90s here, which is 180. That leaves 180 left. That means 60 and 180 will make this one. So this is going to be 120. The other approach to doing that is just going 360 take away 90, take away 90, take away 60, and you will get 120. Okay, so we have used, there are 360 degrees in a quadrilateral. There we go. Now I know this one. If I find this here, I can then move into angles around a point and then do exactly the same process as this kite for this kite here. And what I mean by kite, literally four-sided shape, looks like a kite that floats in the air. Let's have a look. So all these make 160 degrees, so there are 360 degrees around a point. So that's 110 add 120 is 230. So 360 take away, sorry you can't see that, I've added 2 angles there. Taking away 230 from 360 gives me 130, so this is 130. Same reason here, this is 90 and this is 90. That takes off 180 from a four-sided shape, which leaves 180. So this is going to be 50, because these two make 180, so the missing angle is 50 degrees. So BAC equals 50 degrees. Okay, and that's using the angles in the quadrilateral again. Okay, and I think because it's a repeated explanation, I think we'll be fine with that. I think we explained it well enough. Right, this one, make D the subject, so it will say D equals in the end, or something equals D. It's just like solving an equation. We want to unpick this. The E is locked in with the D at the moment. We have to unpick this one, so we're going to take away F and just write it like this. P minus F equals D over E. So if you don't change it, just keep rewriting it. But pretty much the F has gone on the left and it's now a minus. Now I need to get rid of the E, so I'm going to do times by E. So E is times by everything. So P minus F is in brackets because I'm doing everything. And you can take the time to expand it if you wish, but you don't have to. So now D is the subject, and it could be left like this, or it could be left like this. It does not matter. It's been made the subject. Okay, we have a straight line graph and just a few coordinates pointed out. Find the equation of line through X that is perpendicular to AB. So that means it's at 90 degrees to this. Okay, so that is talking to us about the gradient of the line that we've already been given. Okay, so what we need to do is form the equation of the first line and then use that to find the perpendicular line to it. Okay, so let's start. So this is 0, 2, so that's up there at 2. This one is 6, 0, so that's there at 6. Okay, this is 3, 1, so that might come handy later. We don't need it now. And what I need to do is find the equation of this line. So y equals mx plus c. Okay, and then the y-intercept is dead straightforward. That is just literally where it cuts to the y-axis. So the y-axis is here. So that's at 2, and you won't really need that. You need the gradient more than anything. And now we're going to do the gradient, and the gradient is the rise over the run. And you are going to draw a triangle. There's a triangle already here, look. So this is 2, and this is 6. This is the rise, how far up it goes. This is the run. So this is going to be 2 over 6, which is a third. And because it's going this way, it's actually negative a third. So that's the equation of the first line, but you only need the gradient. Okay. Now, if this is the equation of the first line, we use the gradient to find the gradient of the other line. The gradient of a perpendicular line is the reciprocal with the opposite sign. So the reciprocal is the fraction the other way around, so it's 3 over 1. And instead of being a negative, it's now a positive. And I'll just smarten it up, so I don't need the plus, so it's just 3x for now. You don't need the 1 on the bottom. So that's the perpendicular gradient. Okay, and now what we need to do is calculate the sort of the y-intercept, which is here. Okay, so we need to substitute in some values from here. This one right here. So, for example, you've got x is 3 and y is 1, so x is 3, y is 1. So let's set up, so 1 equals 3 times 3, add something, would give us this to balance out, so 1 equals 9, add something. So if I take away 9, this missing something, the y-intercept, would be minus 8. So the equational line is y equals 3x minus 8. I've just realised that it might have been off the video, so we substituted the values in. So x is 3 and y is 1. We didn't know what the intercept was, so you can see I'm just put the intercept back in because I needed the whole equation of the line. So 1 was where the y went, and 3 times 3 is where the x value went, add something. 1 equals 9, add something. I solved the equation, and then the y-intercept was minus 8. So that is the equation of the line. Didn't do a very good job of that one. I wasn't paying that. I was sort of looking out the window, I think. Right, next one. This is nice and straightforward. The maths team reckon that this one might not actually be on the exams. It's just Edexcel have included it, but we'll go through it regardless. Okay, so the way to do to prove that this is a recurring decimal can be written as this fraction is it's like a very systematic process. So we make x equal the recurring fraction, the recurring decimal. Sorry. If I write a little bit out, this will make it clearer to see. Now we have two values that recur. So what we're going to do is multiply by 100. If there were 3 recurring numbers, I would times by 1,000. If there was 1, I would times by 10. Okay, so what we have, and I do it above it because it just makes this a bit easier. So I've got 100x, so I'm going to times this by 100, and it's going to move the decimal point 2 places, so it'll be 17.8787878, and you can see that these are all lined up. And if this is going on for infinity, if it's infinitely long, they're all lined up forever. Okay, so if I subtract them from each other now, what I'll get is all these lined up ones cancelled out, and I'll get 99x equals 17.8 take away 0.1. So you can do that like a little calculation. So 8 take away 1 is 7, and then 17 is not going to be affected. Then going to try and form a fraction, so I'm going to divide by 99. So I get x equals 17.7 over 99. Fractions cannot be left like that, and we're trying to prove that it goes to this. So we need to unpick this a little bit and unpick it and then simplify it. So what we mean by unpick it is get rid of this decimal, and the way to do that is times the top by 10 and times the bottom by 10. Okay. It wants it to be 330, so I can divide the bottom by 3. So if I divide the bottom by 3, that'll be 330. And then 177 divided by 3, hopefully be 59. So 3's into 1 is 0, carry 1. 3's into that is 5, carry 2. And 3's into 27 is 9, so I've got 59. So I've algebraically proven that this decimal can be turned into a fraction. Okay, trapezium. All measurements are shown in centimetres. Work out the area of the trapezium. Give your answer in centimetres squared in the form a root 5 plus b. So there's going to be a root 5 in there, and a and b are just going to be whole numbers. So you have to remember how to find the area of a trapezium. So the area of a trapezium is a half a plus b h, where these are the parallel sides and this is the height. Okay, so it's actually a half times by the parallel sides times by the height. Okay, well, I mean sum of the parallel sides. So we've got a half times by, in brackets, root 5, add root 5 plus 6, multiplied by the height, which is root 5, take away 2. Simplify that down, so it's a half times by 2 root 5. You just add the root 5s to make 2, add 6, root 5, take away 2. And then I've got an expansion to do here, so I'm going to expand this. So I'm going to do that here, and then I'm going to halve it. So the first bit's going to be 2 root 5 times by root 5, take away 2, add 6, root 5, take away 2. I'm going to expand this, so it's going to be 2 root 5 times by root 5, take away 2 root 5 times by 2, and then for this one it's going to be 6 times root 5, so add in, sorry, take away 6 times 2. The root 5s here are going to make 5, so that's 2 times 5, which is 10. Take away 2 root 5 times 2. The 2 and the 2 just multiply together to give you 4 root 5. 6 root 5 is just going to be 6 root 5. And 6 times 2 is 12, so it's take away 12. Like that. We're going to combine them, or collect like terms effectively. So 10 take away 12 is minus 2. And minus 4 root 5. Add 6 root 5 is 2 root 5. Okay, so that is these brackets expanded. So it's a half times by this. And when you times something by a half, you're actually just dividing by 2. So minus 2 divided by 2 is minus 1. And 2 root 5 divided by 2 is just root 5. Okay. Now it's in the right, it's not exactly the right format, so it's actually, if I rearrange it, root 5 take away 1, where A is actually just a whole number 1, you can't see it because you don't need it on the front, and B is actually minus 1. Okay, so you have to remember this part, and it involves a lot of rules for the surd, so I'll use surds and I'll expand brackets and combine surds when you're expanding brackets and divide and so on and so on, so there's quite a bit to it. Okay, so surds is the one to go for if you're not too sure what I was doing there. Right, last one. No, second to last one. Okay, this one, another circle theorem. I wouldn't expect you to have 2 in the same question. Okay, so this is probably going to be difficult or more tricky. So ABCD, they're all points on the circumference, which means we can start setting out like different radiuses, or we could get extra lines in, or assume things about them because they're coming from the circumference. ABC is an equilateral triangle, so that means that these are all 60 degrees, so get those on. OD bisects AB at M, so bisects means it's cut in half. Okay, so that is bang in the middle because it says bisect. Prove that ODA, which doesn't exist yet, ODA, let's have a look, ODA is an equilateral triangle. So this triangle, prove it's equilateral. Okay, give reasons for each stage. So you've got to try and find some way of getting some information. You can't just write these down as 60. You've got to prove that these are going to be 60. And when you've got more complex circle theorem questions, it's actually about adding more information. And the information you can definitely add on these is like extra radiuses. And it's usually about adding extra radiuses on these anyway, or radii on the diagram, to sort of give you more of a starting point. Okay, so if I add another radius this way, I can see a circle theorem coming out here where the angle at the edge is half the angle in the centre, or the angle in the centre is double the angle at the edge. So this is actually 120, because the angle at the centre is double the angle at the circumference. Okay, so that's the first one covered. And then if this is bisecting, that means this is going to be 60, and so is that. So I can prove that one of these angles, at least, is 60. I just need to prove that these two angles here, I'll just colour them in, these two angles here, if I prove they're 60 as well, then it's equilateral. Now, because I've added this line in here, and I already had this line, I can use them to my advantage. They both come from the centre, and they both go out to the edge. They're both the same size. So effectively, I've got an isosceles triangle, like that, where this was the centre. If I just flip the picture around, that's 60 that we've already got. And these two are going to be the same. Okay, so this is an isosceles triangle. So base angles are equal that's obviously good right in there, equal on an isosceles triangle. So this will be 180, take away 60, which is 120, and 120 divided by 2 is 60. So these are both 60. And therefore, I've proved that OAD, because this is OAD, is equilateral, because they've all got 60 degrees. Okay?